Hey there. Okay, so this video is to help you to understand the idea behind atoms sort of swapping places from one molecule to the next to figure out how chemicals are going to change in chemical reactions. So let's start off by defining some of our terms for chemical reactions. In general, there are four different kinds of chemical reactions. There's synthesis, decomposition, single replacement, and double replacement. Now, chemical reactions can get pretty sophisticated, but if you break them down a step at a time, you can usually turn them into a series of these basic chemical reaction building blocks. What are their definitions? A synthesis is when you have some atom, we'll call it A, and some atom B, and they decide to pair up. You have synthesized a chemical based on constituents. For decomposition, well, hopefully you can guess what that is. That's the opposite of synthesis. It's like a divorce of chemicals. Single replacement. For single replacement and double replacement, we're now going to have more than just two. So we may have A and B together, and then another constituent, C. And then after our chemical reaction, we may have A and C plus B. What has happened here is that B has been replaced by C. This is a single replacement. Double replacement occurs when you have two possible candidates. So in one case, for single replacement, essentially only one thing gets a replacement, but for double replacement, two things get a replacement. Now, definitions are all well and good, but examples can sure be helpful. So let's do an example of synthesis. We could have hydrogen gas. So we have hydrogen gas here, and we have oxygen gas. So let's say we have a bunch of hydrogen, maybe, let's say 8 molecules of hydrogen. And let's say we have also nearby some oxygen. So we have, let's say, 4 oxygen gas molecules. If we spark this just right, we can expect them to want to form up differently than they currently are, because they're more comfortable having joined together than they are being apart. We know this by experiment. So we have just enough here. We have twice as much hydrogen as we have oxygen here. So we actually have, if we break this up, we have 16 hydrogen and individual atoms, and we have 8 individual oxygen atoms. And so I'm going to put this in parentheses because you don't actually ever include this in your process on paper. You just think it through. So what this means is that we have 8 possible oxygen atoms that each have 2 hydrogen atoms on them. So we would have then 8 water molecules that can form. This is an example of synthesis because we have, here's A, and here is B, and then by the time we're done, we have AB. Okay? By the same token, we can have something that essentially falls apart, so decomposition. Oops. Now, a great example for this is soda pop. So, you know you have carbonation in sodas, and we tend to think of it as carbon dioxide, but in fact, it is for, you can call it soda or pop or Coke, whatever region you're from. We have carbonation is actually carbonic acid. And this is H2CO3. Okay, so this is not stable. Otherwise, every time you open your Coke, it would stay the same, right? So it tends to fall apart. Now, we had two constituents A and B above, and we called hydrogen our A and oxygen our B. And then we called water molecules our AB. But we chose to call water molecules our AB because we were considering this from a standpoint of what it used to be versus what it is, and it came together to be a water molecule. Here, instead, we can see, if you look carefully, a water molecule somewhere in here. And so if we were to end up with a water molecule, it would not be the entire thing, it would be a piece of it. So here, we need to break this up. So we're going to have a part A and part B that are embedded together. And then when this breaks apart, we're going to end up with a water molecule again. And then, as you can see, if we have our hydrogen is used up and one of our oxygens is used up, well, that leaves us with carbon dioxide. So we're not entirely incorrect when we say that carbon dioxide is part of carbonation. This, then, is AB. The water molecule and the carbon dioxide molecule are one single molecule, and then later they are separate. This is an example of decomposition, whereas before, making the water molecule out of smaller parts was an example of synthesis. Okay, so these hopefully won't be too bad. Single replacement, double replacement should be okay too. It's when you get to large chemical reactions that they start to get a little bit sticky. So let's focus on single replacement. Now, for our example of single replacement, I'm going to tell you about when I was a student, and I had some sodium that I showed to my professor, who was not nearly as cautious and safe and responsible as I am. And he said, let's throw it in some water. And I said, okay, sure, because I guess I was pretty irresponsible at the time. So we throw it in water, and if you know anything about sodium, or if you were listening to me in class when I told you what happens to anything in group 1 when you put it in water, it catches on fire. It's not stable, so of course we ended up with a little bit of a mess. We expected it to catch on fire, but what we didn't expect was for it to explode. So it burned for a little while, and burned and burned and burned, and then it went pow and blew up. So we had to stop and think about why. And after we actually thought about it, which in retrospect would have been a good thing to do before we threw it in the water, we decided that we understood that this was actually a single replacement reaction. Let's look at it carefully. Sodium. We have a large chunk of it, so let's give ourselves, say, 12 atoms. 12 is a good place to start because, you know, it's divisible by 2, it's divisible by 3, it's divisible by 4, it's divisible by 6. You're probably going to be able to get something out of that. So we have a bunch of sodium, and we also have a bunch of water. Now we may need to add some water molecules here, but I'm going to go ahead and put H2O, and then however much we need in front of that. Maybe we'll go ahead and put, I don't know, let's say 6. We may need more. We will. So what happens is that the sodium has a tendency to break apart in the water, and when it does, that sodium grabs the one oxygen and one hydrogen and forms sodium hydroxide. So sodium hydroxide, let's see, that means that one sodium and one oxygen form up. We've only got 12 sodium, we have 12 sodium and we only have 6 oxygens, so we're clearly going to need to make more water molecules to react with our sodium. So let's do that. Let's make 12. Now we could have started with 2 or 1 or whatever, but I just wanted to throw a number out there so that we could balance it out. So that means we started off with 12 sodium atoms, and we started off with 12 oxygen atoms, and we started off with 24 hydrogen atoms. So we have stolen 12 of the 24 hydrogen atoms to go to our sodium hydroxide. And in the process, we have ended up with a leftover. And that leftover is this hydrogen. So we end up with 12 hydrogen atoms. Now those hydrogen atoms are not going to stay atoms for very long. They're going to form up as a molecule, but for right now we're interested in this replacement reaction. So let's write this out very carefully. We have sodium, we don't actually need the 12 there, sodium plus H2O becomes sodium OH plus H. So essentially what has happened here is that the water molecule, H2O, has taken one of its hydrogens and left it behind and grabbed a sodium in its place. This is a single replacement reaction. Here we have OH with another H, which is a water molecule, and sodium turn into sodium, which was C, OH, which was A, and hydrogen, which was B. So, as you can see here, if we break it apart into marbles like you did in your lab, then you can actually turn this into groups that show a single replacement reaction. On to our story. What happens to our hydrogen? Well, now that we have hydrogen, it's time for another reaction. That hydrogen is not happy being by itself, so it's going to form up, and what is that? It's a synthesis. So we have a secondary reaction taking place here, a synthesis reaction. That is going to be, since there are 12 hydrogens, and we can look up, or maybe we can reason through using the periodic chart, that hydrogen will form up to be 2 hydrogens per molecule, hydrogen gas. So that would give us 6 hydrogen molecules, each of which is H2. So the reason that this exploded was because it released hydrogen gas in the midst of a flame, and then the hydrogen gas caught fire and exploded. So, interesting. We were witnessing this first reaction first as this was burning, and then when we accumulated some hydrogen, then that produced a second reaction, and those were very visible to us. Okay, so this is single replacement. We have, and we can write this in color as well here. So we have our water molecule is H2O, but I'm writing it as 2 parts because we know we're about to lose part of that. And we have our sodium atom here as well. And then do we still have the sodium part of the story? And you have the hydrogen part of the story, and they have swapped places. Okay, single replacement. Now on to double replacement. Okay, for our double replacement, we're going to look at something very simple. So we have, let's say, magnesium oxide and calcium sulfide. So in this case, they're not as comfortable as they could be, so they will undergo a double replacement. Let's go ahead and change our colors here. So we'll have oxygen, and we'll have calcium. Oops. And we'll have, of course, sulfur has to be yellow. Okay, so well, that kind of looks like Mg, doesn't it? To replace Mg, might as well make it white. Okay. There we go. Alright, so this reaction is going to be pretty straightforward. Essentially what happens is the magnesium then prefers a sulfur. So we're going to get magnesium sulfide. Now, which one would it, which one could you expect it to be? Well, that you have to look at your periodic table to determine. Magnesium and calcium are both over on the left side of the periodic table, so you would expect them not to be so inclined to be partners. So this is clearly just a swap of ion. And then calcium, plus calcium oxide. So as you can see here, essentially all we've done is swapped a group 6 for a different group 6, oxygen for sulfur. Okay, 1 for 1. It is possible, of course, that we could end up with something that is O2, and it could end up swapping in other ways. So it isn't necessary that it be one atom and one atom. So as we saw in the single replacement reaction. But this is the general idea behind double replacement. So now we can actually look at any kind of reaction and piece it together based on these basic building blocks. Let's look at one that is particularly dangerous in the household. Now, you hopefully have been told never to mix bleach and ammonia, and we're about to find out why. Chlorine bleach, to be specific, and the formula for chlorine bleach is sodium, oxygen, chlorine. And ammonia is actually ammonium hydroxide, so that is going to be some stuff. And then a hydroxide. Now hopefully you may remember that word hydroxide. Hopefully it's ringing a bell. In fact, hydroxide means this is a base. And this is also, in fact, a base. So things don't actually have to be acids and bases in order to react with each other. They just have to be, reactive. And we're about to find out how that works here. So in fact, what's going on here is that you have an oxygen and a chlorine that have managed to kind of find one another but are still missing an electron, and a sodium that's hanging by. And over here, you're having a nitrogen with 3 hydrogens, and that is also positive. And then it's going to have a little hydroxide ion just sort of hanging nearby. And so what's going to occur first is a very simple double replacement where we have these 4 A, B, C, D. And our double replacement is going to form our ever-popular sodium hydroxide. So this will become sodium hydroxide plus, I don't usually put the arrow this way, but I ran out of room over here, so but this will form sodium hydroxide. And then what are the other ones? We've taken A, B, and C, D and formed A, D, so we now have B, C for our double replacement. So that's going to be this. And now we're going to have a secondary reaction because this is not very stable. So this is actually going to decompose. I'm going to leave out the sodium hydroxide now because it's no longer part of the secondary reaction. So this is going to decompose. Now look here, we have H3 and an O, and those sure would like to be a water molecule, so let's go ahead and let those be a water molecule. And what is left is a nitrogen atom, a hydrogen atom, and a chlorine atom. This is known as chloramine gas and will kill you. So that is why it's not a good idea to mix bleach and ammonia. You will end up with sodium hydroxide, which is, not the tastiest thing in the world, not good for you, don't eat it, it will hurt you. Water, which is not so bad, we like that. And then chloramine, which is, you'll breathe it and it will harm you. So definitely make sure that you store the bleach and the ammonia in different places. Okay, so hopefully this isn't too overwhelming. I'm just providing examples. You will not be required to know how to perform a chemical reaction, but I do want you to understand the idea behind a single replacement or behind a double replacement. If I show you a chemical reaction, you should be able to tell me whether it's a single replacement or a double replacement. Okay? If you've got any questions, please let me know, and I'll see you in class.